Welcome to a tutorial on circuit theory, and today we're here to discuss about the maximum power transfer. Okay, that's the maximum power transfer theorem. Okay, so there you go. Now, well, in this particular theorem that we have here in case of circuit theory, basically, states that the maximum power that we need to deliver to a load, okay, will only be possible if the load resistance is equal to the internal resistance of the DC network that is supplying the power. So based on that, here we have the formal statement as you'll come across in various textbooks, which says that the resistance load, okay, that's the load resistance that we're talking about. Okay, so the resistance load being connected to a DC network receives maximum power when the load resistance is equal to the internal resistance. That's of course the Thevenin's equivalent resistance over here. So the resistance load being connected to a DC network receives maximum power when the load resistance is connected to, or rather is equal to, the internal resistance, that's the Thevenin's equivalent resistance of the same source network as seen from the load terminals. Okay, so that basically gives us a conclusion about maximum power being transferred to a resistance load. Okay, and in order to do that, the load resistance must be equal to the Thevenin's equivalent resistance of the DC network that is supplying the power to the specific load resistance under discussion. Okay, so we can just represent this thing, or rather, if we just apply this theorem to a network. Okay, so we can, by doing that, we can basically simplify a network in in terms of Thevenin's theorem. We know that previously from our tutorials on Thevenin's theorem and all. Okay, so based on that, we could basically diagrammatically represent this statement as something like this. So there's our DC source network, and if we need to transfer the maximum power to a load resistance, let's say this is the load resistance in pink connected to the DC network, then we need to basically make this load resistance equivalent to the equivalent Thevenin's resistance of this DC source network over here. Okay, so based on this theorem, we can basically prove this theorem. So let's just in order to prove the theorem, okay, we just assume that we have an electrical network, something like this, as I'm going to show you over here. There you go. So let's just assume that here we had some kind of a network, some kind of circuit over here. Let's say this DC network, the DC source network that we're basically talking about over here. Let's say this is that particular DC source network, okay, simplified using Thevenin's theorem, the one outlined in white. Okay, so it's been simplified using Thevenin's theorem to basically representing this whole DC network by means of only a voltage source and a resistance. So it just consists of a equivalent voltage source, okay, and the equivalent resistance of this source network. So let's say this we simplify a network, okay. So let's just imagine that we had a network over here that is basically being simplified with Thevenin's theorem to represent it in somewhat this way, and now we have here a load resistance across which we'd obtain, or rather to which we'll basically transfer power from this network, DC network circuit. Okay, so let's just use the theorem, or rather let's just go for the proof of this theorem. Okay, so if we just consider this equivalent circuit, okay, using where this DC network has been just reduced by means of Thevenin's theorem. So if you just consider the circuit over here, then with the load resistance connected, which is of course, as you can see, a variable resistance over here, that's a load resistance RL, as you can see. So in this circuit, we'll basically be having a certain amount of current flowing within the circuit due to this source voltage being connected over here named as Vs. Okay, so now this current would basically be flowing through the equivalent Thevenin's resistance of the DC source network, okay, as well as through the load resistance. So basically the total amount of current that should flow in this circuit would be basically given as something like this mathematically. Okay, it'll be given by Vs divided by RTh plus RL. Okay, so that's the equivalent amount of current that should flow through this circuit. And now we need to find out the power that would be dissipated across this load resistance. Okay, so for that we know that the power dissipated across the load resistance is basically given by I square RL. Okay, so where RL is of course the load resistance and I is the amount of current that should flow through, I mean that is basically going to flow through the load resistance and the circuit as well. So calculating that, we are getting something like this. We get Vs, if we just substitute the value of current right from this relationship of the current that we've obtained a little while ago. So Vs divided by RTh plus RL squared multiplied by the load resistance RL. Okay, so this is basically the amount of power that needs to be dissipated across, or rather that will be actually dissipated across this load resistance. Now here we need to make sure that this power is the maximum amount of power that should be transferred from this voltage source to the load resistance. Well, in order to do that, as you can see that here the RL is a variable resistor, so by varying RL we could basically change the amount of current that should flow through this load resistance. So with that we can obviously affect the amount of power that would be dissipated across this load resistance as well. So in order for this power that would be dissipated across the load resistance, okay, in order to just make this PL, that's the load power, okay, dissipation maximum, we need to ensure that dP by DRL, okay, so sorry there, that's dPL by DRL, applying calculus, this is equals to 0. Okay, so this is the basic, or rather the necessary condition for maximum power transfer. So I'll just write it down over here. So this is actually the maximum power transfer condition. Okay, so there you go. So just keeping that in mind, we first need to find out what is dPL by DRL for this particular equivalent network that we are dealing with. Okay, so from this network, if we just try and find out dPL by DRL, okay, from this relationship of the power that we had obtained here a little while ago, then we're basically gonna get something like this. Okay, I'll just write it down in a very short while. So this is exactly the relationship, or rather the expression that we're gonna obtain if we just try to find out dPL by DRL, okay, from this relationship of PL, that's the load power dissipation. Okay, so now this is basically obtained by applying calculus. Okay, you'll have already learned that in your high school, so that's not going to be a problem at all. So by simplifying this whole thing, we're basically going to get something like this. We're going to get VO square, sorry there, it's going to be VS square, sorry that's my mistake over here, so I'm just going to rectify them. Okay, so that's better. That's Vs square multiplied by RTh minus RL by RTh plus RL whole cube. Okay, so just by simplifying this above, this mammoth expression over here, we're basically be obtaining this shorter expression right over here. That's exactly that we have what we have written down. Okay, so here, as you can see in this from this expression, we need to put dPL by DRL, this whole ratio, equal to 0. So since we found out the value of dPL by DRL, we're just putting this equal to 0. So therefore, by putting, okay, so we're just gonna write it down over here. So by putting, okay, dPL by DRL equals to 0, we're basically gonna get something like this. This is Vs square, okay, that's right, multiplied by RTh minus RL by RTh plus RL whole cube is basically equals to 0. So by simplifying this whole thing, okay, we obtain, or rather come to the conclusion that RTH is equals to RL. So this is exactly what is basically stated in the above theorem statement. Okay, as you can see, it needs to be equal to the internal resistance, or rather the Thevenin's equivalent resistance of the DC source network, which is driving the load resistance. Okay, so just that keeping in mind, okay, since we've obtained that, so let's just find out as to what amount of power would be transferred to the load. I mean the magnitude of the power that would be transferred to the load, okay, if we kept RL equals to RTH. So if we would just go back to our network once again, so over here we can see that if we just go forward and replace RL with RTH, we'll get the load power dissipation. Okay, so once again I'll write it down. So we know that PL is basically equals to VS by RTH plus RL whole squared multiplied by the load resistance over here. And now if we put RL equals to RTH, then we're basically going to get VS square by and since we're putting RL equals to RTH, okay, so in that case we'll get in the denominator as something like 2RTH, and then it'll be squared and we'll get 4RTH square, and multiplied by RTH again, since we're putting RTH in place of RL. Okay, so we're basically going to get VS squared by 4RTH. So that is exactly the value of the power that would be transferred to the load resistance right in this network over here. So if we would basically find out the total power, then we could basically find out the efficiency. Okay, so here the total amount of power that would be taken by the circuit would be given by this relationship, as we can show over here. So since the entire resistance of the network is of course the load resistance and the sum of the load resistance as well as the equivalent Thevenin's resistance, that's the internal resistance of the DC network. So if we just go forward and put their values over here, we're going to get VS by RTH plus RL squared, okay, multiplied by RTH plus RL. And now if we just put RL equals to RTH in this relationship, we're basically going to get something like VS squared by 4 RTH multiplied by 2 RTH right over here. So now we just cancel these terms and cancel RTH. Sorry, it's going to be squared over here as well. So we're going to get VS squared by 2 RTH. Okay, and now here's the total power dissipation in the entire circuit, okay, and we're basically going to compare it with the power dissipated in case of the load resistance only. Okay, so there goes our efficiency over here. So we're going to find out the efficiency is basically going to be the load power dissipation divided by the total power dissipation multiplied by 100. So here if we just go forward and put their values, okay, over here we got PL is equals to VS squared by 4 RTH, and down below we're going to get the total power dissipation as VS squared by 2 RTH, and that multiplied by 100 basically results in the cancellation of the VS squared terms, the RTH, and on top of that we'll be basically left with 2 by 4 multiplied by 100. So if we just do that, we're basically going to land up with 50% of efficiency. So by utilizing maximum power transfer theorem, we can basically find out that the maximum power that could be supplied to a load resistor by a circuit network, okay, that is basically reduced by the Thevenin's theorem, okay, it's going to be 50% at the most. Okay, so having said that and described the theorem in detail, we just come to the end of our tutorial discussion on the maximum power transfer theorem. So I guess you'll have gone through the theorem and have understood that pretty well. So don't forget to watch our next tutorials on circuit theory. So till then, it's just going to be a very short goodbye, and thanks for watching.